Alright? Then let's have a summary here. So this is how we calculate the electron and hole density in the semiconductor. N equals to NC times this exponential function. This is due to the Fermi statistics. And P equals to NV times this Fermi function. So be careful, the EF. One is EF minus EC, one is EV minus EF. But as I said, it's easier for you to remember this if you think that it's a distance. And this distance is always relative. So why is that? Because EC, EV, and your EF. So you can always get this delta E plug into here. EF is lower than EC, so it's a negative number. And then for here, you can always get another delta E, and you can plug in here. And remember, EV is lower than EF, so this delta E is another negative number here. And for silicon, NC and NV are constants next to those numbers. Any questions? Alright, so let's look at the intrinsic semiconductor. So intrinsic semiconductor means without doping. Let's say pure silicon, no doping. So if low doping, then where is the Fermi level? So it's in the middle of the band gap, almost the middle, I would say. But you can derive this because intrinsic silicon means what? Means N equals to P. So I can do it on board. Maybe you can turn the camera here. So let's do. Okay, so the intrinsic means N equals to P. Because intrinsic silicon, you know, the way you generate the electron and hole pair is broken of that bond. So once you get one electron, you get one hole. So N equals to P. So if N equals to P, then you can get the NC exponential the EF minus EC over KT equals to the NV exponential EF minus EV. Sorry, EV minus EF over KT. So then, if you think roughly the NC equals to NV, of course there are small differences there. For the silicon, one is like 1.08, one is 2.8. But if you think they are similar, because you need to take the log scale. After you take the log scale, this is very close to each other. So if you do this, then you will take the log scale of both sides. Then EF minus EC will equals to EV minus EF. So you will get EF is half of the EC plus EV. So that means for the intrinsic silicon, the Fermi level is in the middle of the band gap. Any questions here?
So it's approximately in the middle, not exactly.
Not exactly, but if you calculate the number, it's almost in the middle. Because when you take the log scale, what matters is the magnitude of the 10 to the power 19 or 10 to the power 18, as long as they are on the same order. After you take the log scale, they will be roughly the same.
And NC and NV are thermal constants?
Yeah, for silicon, yes.
For a particular material.
Of course, for different materials, those numbers are different.
And it does not depend on temperature?
No. Okay, so this is the Fermi level in the middle. And the other thing we want to derive here is the intrinsic carrier density. So for the intrinsic silicon, let's look at the NP product, N times P, NP product. So if NP, if you use those two equations, NC E and EF minus EC over KT times this NV exponential EV minus EF and then over KT. So if you do this, you can get NC NV here and the exponential term EF minus EC plus EV minus EF over KT. You just combine the exponential terms together. So you will see that the EF will cancel each other. So what is left is NC NV exponential negative EC minus EV over KT. So what is the EC minus EV? You see the energy diagram, right? EC, EV, you have EF in the middle. So EC minus EV will be the EG, the band gap. So here you will have the NC, NV, E, the band gap over KT. So you see that the NP products are all constants here, because NC, NV, silicon parameters, EG, also the silicon parameter. Of course, this depends on the temperature. But there's no EF in this equation. So for intrinsic silicon, as we just discussed, N equals to P. And we define this as intrinsic carrier density, Ni. This I represents intrinsic. Okay. So then you can get the basically it will become Ni squared equals to this guy. because NP now becomes Ni squared. So Ni will be square root of NC NV, and then you know for the square root of the exponential function is just divided by 2 there. So the Ni is given by this equation. And if you really plug in the numbers for NC, NV, and the EG, and then assume the room temperature, you will get that number you have seen before. It's 1.5 times 10 to the power 10 centimeter per centimeter cube. So you have seen this number in the previous lecture. We talked about that. At the room temperature, the free carrier density is this number, and it's roughly 1 out of 10 to the power 13 bonds are broken. So this gives you this intrinsic carrier density. So any questions here? So this is without doping. You get this carrier density. And in the next lecture, we will talk about after you do the doping. Basically, you are going to moving up and down the Fermi level. And then you can tune the electron density and hole density. You can make one larger than the other. For example, if you do N-type doping, right, you have more electrons, less holes. But no matter what, okay, no matter what doping you do, if you look at the NP product, it will be a constant. All right. So I think that's for today's lecture. And if there are no more questions, we will meet